Salam, peace be upon you. My name is Muhammad Laif Sabigi, the father of Holophase. Part 12 Wave Packet Generation How the Language Writes Localized Ripples. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. You are walking the paths of Book 9.3 in Episode 9, The Generative Grammar. Our journey into the realm of waves and fields has begun. In our last climb, we discovered the foundational rule of this book, dispersion. We learned that a medium, a particular stable paragraph in the phi story, acts like an organ pipe, allowing only specific marriages between temporal rhythm, omega, and spatial pattern, k. This dispersion relation is the grammar for pure tones, the infinite perfect sine waves that resonate forever. But if you stop and listen to the world, you do not hear infinite pure tones. You hear a bird's chirp, a brief, localized trill that starts and ends. You see a ripple from a dropped pebble, a localized bump that travels outward and fades. Reality is written not in endless sine waves, but in packets, brief, localized bundles of disturbance that have a birthplace, a journey, and a dissolution. Today, in Wave Packet Generation, How the Language Writes Localised Ripples, we make a crucial leap from the abstract grammar of allowed tones to the tangible physics of real signals. Our anchor image is a single, clean raindrop falling onto the still surface of a pond. Picture it in your mind. The moment of impact is a singular event in time, a pinpoint in space. From that event, a circular wave emerges, not a single, perfect ripple extending to infinity, but a compact group of ripples, a packet. You can follow this packet with your mind's eye. It has a center that moves outward. Its sharp initial definition softens, it spreads. Its energy, once concentrated, diffuses. This packet is a sentence in the language of water, a sentence with a subject, the disturbance, a verb, propagates, and an adjective that changes over time, spreading. Today, we learn how the holophase language composes such sentences. We learn how a localized bump in phi, filtered through the dispersion relation of its medium, inevitably becomes a traveling, evolving wave packet whose entire destiny, its speed, its spreading, its distortion, is written in advance by the grammar. Here is the practical puzzle of this part. We now have a rulebook, the dispersion relation, omega as a function of k, that tells us which pure sine waves are allowed in a medium. But a localized bump, like our raindrop splash, is not a pure sine wave. Mathematically, it is a sum, a mixture of many different pure sine waves, each with its own omega and k. So, if we create such a bump in the phi field, what happens? How does this mixture of allowed waves conspire to produce a moving, breathing, living packet? Can we predict its behavior just from the dispersion rulebook? The answer is a definitive yes, and it reveals one of the most elegant constructions in the wave-generating grammar. A localized initial bump is a superposition, a sum, of many pure wave modes. Each of these component modes travels according to the dispersion relation. But here is the magic. They travel at different speeds. The speed of a pure mode is its phase velocity, which is omega divided by k. But the speed of the overall packet, the lump, is not the phase velocity. It is the group velocity. This is a new kind of speed, defined as the derivative of omega with respect to k. For our ears, if the dispersion relation, omega of k, is a curve, the group velocity is its slope at a given point. This is the first key to packet motion. The different wave components, traveling at slightly different phase velocities, will interfere with each other. Their interference pattern is what we perceive as the packet. And the point of maximum constructive interference, the peak of the lump, moves at the group velocity. So, our first prediction: the center of a wave packet travels at the group velocity, a speed dictated by the slope of the dispersion curve at the packet's central frequency. But there is more. Because the different component waves travel at different speeds, they will also spread apart over time. The initially tight bundle of waves will disperse. A packet of light in a prism spreads into a rainbow. A sharp sound pulse in air becomes a dull rumble. This spreading is not random. It is precisely governed by the curvature of the dispersion relation. The second derivative of omega with respect to k, how the slope itself changes, determines the rate of spreading. A straight line dispersion relation, where omega is directly proportional to k, has zero curvature and produces non-dispersive packets. They travel without spreading, like a perfect pulse of sound in air under ideal conditions. A curved dispersion relation produces dispersive packets. They spread. Their width grows with time in a predictable way. So, our second prediction: the spreading or focusing of a wave packet is dictated by the curvature of the dispersion relation. Let's listen to the triunity of wave packet generation. The time echo of packet generation, the life cycle of a disturbance. A wave packet has a birth, life, and death in time. It begins as a localized event, a sudden change in phi at a specific moment. This is its temporal birth. Its life is its propagation. The center moves, the shape evolves. Its death is its eventual dissolution through spreading or absorption, where the localized energy is so diffused it becomes indistinguishable from the background. The time echo is this narrative arc of the packet. The dispersion relation writes this arc script, determining how long the packet remains coherent, how quickly its peak moves through the timeline, and how rapidly its identity, its localized shape, fades into the noise of the medium. The space echo of packet generation, the evolution of a shape. Initially, the packet has a specific spatial profile: a Gaussian bell curve, a square pulse, a splash pattern. As time passes, this shape transforms. It may widen, its sides may develop oscillatory wings, its peak may diminish. This spatial evolution is not arbitrary. It is the direct, visible result of each Fourier component, each pure sine wave in the mixture, traveling with its own phase velocity. The space echo is this morphing silhouette. It is the footprint of the packet's history, a visual record of how the medium's dispersion properties have acted upon the initial condition. You can read the dispersion relation in the changing shape of the packet. The motion echo of packet generation, trajectory and dispersion. This combines time and space into observable kinematics. The motion of the packet center, the group velocity, and the motion of its boundaries, the spreading, are the primary verbs. In a non-dispersive medium, the packet moves as a rigid, unchanging lump. In a dispersive medium, it moves like a puff of smoke, its center drifting while its edges billow out. The motion echo is this dual choreography, translation plus deformation. It answers practical questions. How long will a signal take to arrive? How much will it have blurred by the time it gets there? This is the essence of communication and signal processing, rooted in the grammar of phi. Now, let's locate this powerful node on the master tree. We are on the wave packet synthesis branch within book 9.3, Waves and Fields. This branch depends critically on the node of dispersion relations. Without knowing omega of k, you cannot compute group velocity or spreading. It enables the next major steps: understanding interference when packets overlap, and coherent field formation when many packets or waves lockstep. It is also the crucial bridge to quantum mechanics, where particle wave functions are fundamentally described by wave packets. Here, in the classical wave realm, we build the conceptual machinery for localized traveling entities. To illuminate this, let's scatter our lanterns wisely. A near lantern from the kitchen. A drop of food coloring in still water. The moment the drop hits, you see a highly localized, intense blob of color. This is your initial packet of dye concentration. It does not stay a perfect blob. It begins to move. It drifts with any subtle currents, the group velocity of the fluid flow. And it spreads. It diffuses. The sharp edges become fuzzy. The blob grows into a soft cloud. The rate of this spreading is governed by the dispersion relation for diffusion, which is different from wave dispersion, but obeys the same logical structure. An initial localized disturbance evolves predictably based on the constitutive rules of the medium, in this case, the viscosity and molecular motion of water. You can predict the size of the cloud after a given time. A middle lantern from telecommunications. A digital pulse in a fiber optic cable. When you send a bit of information, a short, bright pulse of light, down a glass fiber, you are injecting a wave packet. The fiber is a dispersive medium for light. Different colors, different omegas within the pulse travel at slightly different speeds due to the dispersion relation of the glass. If unchecked, this would cause the pulse to spread, smearing into the neighboring time slots and creating errors. This is called dispersion penalty. Engineers must carefully design the fiber and use compensating elements to manage this spreading, precisely calculating it from the known dispersion relation. The group velocity determines the pulse's travel time, the latency. The dispersion curvature determines how much it broadens. The entire technology of global internet rests on mastering the grammar of wave packet generation in a specific medium. A far lantern from quantum mechanics, the electron wave packet. In the quantum description, an electron is not a point, but is described by a wave function, a complex valued field that behaves like a wave packet in the phi field of possibility. When an electron is emitted from a source, it is localized. This wave packet propagates. According to the quantum dispersion relation, which links energy to momentum, or omega to k, the packet spreads. This is not just a theoretical idea. In stunning experiments like the double-slit experiment with single electrons, the electron is detected as a localized particle, a dot on a screen, but over many repetitions, the pattern of dots builds up an interference pattern that proves the electron's wave function. Its probability packet spread out and went through both slits, interfering with itself. The spreading of the quantum wave packet is a direct, observable consequence of the dispersion relation written by the Schrödinger equation, which in our view is a particular dialect of the Holophase grammar. From the diffusing dye to the broadening light pulse to the spreading electron wave, a universal theme, localization in space requires a mixture of frequencies. The medium's dispersion relation then dictates how that mixture evolves in time, how it moves, how it blurs, how it holds together or falls apart. What then is the specific language role of wave packet generation? It is the production rule for localized verbs. It is the grammatical procedure that takes an initial condition, a localized noun phrase, a bump, and the dispersion rulebook, the adverbial conjugation table, and generates the complete sentence of its temporal evolution. A verb phrase with a speed, a direction, and a manner of change, spreading. It translates a static, what is here now, into a dynamic, what will happen there later. The core question this part asks about phi is, Given a localized initial configuration of the phi field, and given the dispersion relation omega of k that characterizes the medium, what is the complete future history of that configuration? How does it propagate and evolve? We are moving from the grammar of possibilities, allowed waves, to the grammar of actualities, time evolution of specific disturbances. What does this packet generation rule do in the generative process? It initial conditions into dynamical predictions. It quantifies signal integrity, predicting how much a message will distort over distance. It provides the classical precursor to the concept of a quantum particle's wave function and its evolution. It demonstrates how macroscopic lamp-like behavior emerges from the coherent superposition of microscopic wave rules. Now, stability and breakdown. The linear wave packet theory we've described is stable and predictable for small amplitude packets in uniform linear media. It holds as long as the superposition principle holds, meaning waves don't interact with each other. It breaks down due to two main effects: nonlinearity and inhomogeneity. In a nonlinear medium, a wave packet can distort in ways not captured by simple dispersion. It can steepen into a shock wave or split into solitons, stable, non-spreading packets that balance dispersion against nonlinearity. In an inhomogeneous medium, where properties change with location, the group velocity itself becomes position-dependent, bending the packet's trajectory. Within its domain, linear uniform media, the packet generation rules are as reliable as arithmetic. This brings us to the cornerstone of our method: falsifiability. The claim that wave packet dynamics are wholly determined by the dispersion relation derived from the phi field is a precise, quantitative proposal. The central claim: for a given medium modeled by a specific phi configuration, if you prepare a wave packet with a known initial shape and central frequency, its subsequent motion and deformation will be fully predicted by the dispersion relation omega of k. The center will move at the calculated group velocity. The width will spread or focus at the rate determined by the dispersion curvature. Measured trajectories and spreading rates for a variety of packet types must match these predictions within experimental error. Concrete measurement scene. Consider ultrasound waves in water. We set up a large water tank. Using a piezoelectric transducer, we generate a brief, localized ultrasonic pulse, a wave packet with a central frequency of, say, 1 MHz and a Gaussian envelope. We use an array of hydrophones, underwater microphones, positioned at known distances to record the pulse as it passes. From the recorded data, we can track, first, the time of arrival of the pulse peak at each hydrophone, allowing us to measure the group velocity. Second, the changing shape of the pulse, how its duration, its width in time, increases with distance, allowing us to measure the spreading rate. We repeat this for pulses with different central frequencies and different initial widths. The pass condition, validation. The measured group velocity matches the value obtained by taking the derivative of the independently measured dispersion relation for sound in water, which is nearly constant, so group velocity equals phase velocity. The measured pulse spreading matches the prediction from the dispersion curvature, which for sound in pure water is very small, leading to minimal spreading. If we change the medium, for instance, by adding microscopic bubbles to the water, which drastically alters the dispersion relation, the predictions change. The new measurements on the bubbly water should then match the new group velocity and spreading rates derived from the new dispersion relation of the bubbly fluid. The phi model for the bubbly medium, which incorporates the bubble resonance, successfully predicts the novel packet behavior. The fail condition, falsification. The packet consistently moves at a speed significantly different from the predicted group velocity, even after accounting for all known experimental errors. Or, The packet spreads at a rate that cannot be reconciled with any possible curvature of the dispersion relation derived from the phi model. Most strikingly, if we observe a packet that focuses, gets narrower, in a homogeneous linear medium where the dispersion curvature predicts only spreading, the theory is broken. Such anomalous behavior would force a major revision of the phi grammar for that system, perhaps indicating hidden nonlinearities or new physical effects not captured by the linear dispersion model. This falsifiability ensures our elegant wave packet synthesis remains accountable to the nuanced, sometimes messy, behavior of real waves. Let's now cultivate a practical recognition skill. You can train your mind to see packet generation logic in any scenario where a localized event or lump moves and changes shape over time, and where the rules of the environment dictate that change. Listen and imagine a gust of wind moving across a field of tall grass. The gust is a localized packet of air momentum. You can imagine its leading edge, the center, moving at a certain speed. As it moves, it also spreads out and weakens. Its energy dissipates into the surrounding still air. The dispersion relation here is governed by fluid turbulence and viscosity. Observe in your mind the travel of a news headline through a population. The news breaks, a localized event. It first travels quickly through highly connected networks, high group velocity. Then, as it reaches different communities with different propagation characteristics, it spreads, mutates, and its shape, the details of the story, distorts. The social medium has a complex dispersion relation for information. Consider a traffic jam forming and propagating on a highway. The jam is a localized packet of high density. Its front moves upstream at a characteristic speed, the group velocity of the density wave. The jam itself may widen or shrink over time, depending on the inflow and outflow rates. This is its spreading, governed by the fundamental rules of traffic flow, its dispersion relation. When you perceive a distinct thing that moves, but also breathes, that has an identity which both translates and transforms, you are likely conceiving of a wave packet. Its behavior is a dialogue between its initial composition and the grammatical rules of the stage it moves upon. We must connect this deeply to our holophase journey. In the previous part, dispersion gave us the alphabet of pure waves. Here, packet generation shows us how to form words and sentences from that alphabet. A word is a localized combination of letters. Its meaning, its evolution, is determined by the grammatical rules, dispersion, acting on each letter. We haven't added new physics. We've simply applied the existing grammar to a more interesting initial condition. This is the generative engine at work. Start with a pattern, apply the rules, unfold the story. If you want to see the full mathematical derivations and exact equations behind this idea, the Fourier synthesis of packets, the method of stationary phase for deriving group velocity, the detailed calculation of dispersion-induced spreading, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Let's pause and survey our ascent in book 9.3. We began with the abstract filter of dispersion. We have now learned how to use that filter to generate dynamic, localized entities, wave packets. We can predict their motion and evolution. This is a massive step. We now possess the tools to describe how signals, pulses, and localized energy move through the world. But we are still describing single sentences. What happens when two such sentences meet? When two wave packets cross paths? This brings us to the doorstep of one of the most beautiful phenomena in wave physics: interference. In the next part, we will see how the holophase language writes paragraphs of overlapping waves, creating patterns of light and dark, reinforcement and cancellation that form the basis of holography, interferometry, and the coherence of lasers. Before we end, the mandatory zoom out to hold our scope. The wave packet, for all its richness, is still just a specific pattern in phi and its derivatives. Its generation and evolution are computed using only the dispersion relation, which is itself a rule about omega and k, the first shadows of phi's change. We have added no new substances. We have simply learned a powerful grammatical procedure, a recipe within the language. One field, phi, plus its infinite tower of derivative questions. In this episode, we have journeyed from the first sentence through topological production, knots and braids, and now deep into wave production, where we can write localized traveling ripples with predictable fates. The grammar is showing its capacity to generate the stories of motion and signal that fill our experienced reality. As we conclude, hold the image of the raindrop and the pond. The drop is the initial condition, a punctuation mark in the field of water. The pond's properties, its depth, its surface tension, are the dispersion relation, the medium's grammar. The resulting circular wave packet is the sentence written by their interaction. You can imagine the sentence unfolding. The leading ripple, the group velocity, races outward, while the whole structure gently broadens, disperses. It is a complete, elegant thought in the language of fluid. The universe is an infinite pond, and every event, every photon emitted, every sound made, every particle created is such a raindrop. The holophase field is the fundamental fluid, and the wave packet generation rule is the universal syntax that translates the splash of existence into the traveling, evolving story of what happens next. Salam and peace be upon you.